Welcome to Intro to Functional Programming in Haskell. Today we're going to be talking about algebraic data types and practical uses for them. Within the Haskell language, we often define new data types to make expressing our programs easier. This helps make our code more composable and pleasurable to read. So newly defined data types can be the product of other types or the sum of other types. Now, these other types can either be concrete or polymorphic. For example, a simple product type is shown here. It can basically take on a value that contains two values of some other type, and the two values must be of the same type. A simple sum type is divided up into options. A simple example is the bool type. It can either be true or false. Now, this sum type could take a type level argument like the previous product type, but we'll get to that in a moment. So, when you're working in more complex situations, often new data types will actually be a combination of products and sums, and those products and sums might actually be further combinations of products and sums. A useful metric for helping understand the complexity of the code you're working in is the number of possible values the types you're working with can take on. This can be calculated by adding up the number of possible values for summed types and multiplying out the possible manipulable values of product types. For example, here in this example data type, it can either be a pair of bools, or it can just simply be this something else value, or it can be this something else 2 value. So the total number of possible values is the total number of possible values that the first option can be, plus the total number of possibilities for the second, plus the total number of possibilities for the third. The second and the third options each can only be one thing, the simple something else 1 and the something else 2. The first possibility, the pair of bools, has 4 possible values. It can be true or false in the first slot, and it can be true or false in the second slot. So it has 2 times 2 or 4 possible values. So this example data type can be up to at 6 different values. As you may have noticed, some types require a type level argument. These type level arguments help these types realize what they truly are. The concept that encompasses this need for a type level argument is kinds. Kinds are types for types. For example, you can have just an int or a char. You can have a variable m set to the number 12, but you can't just have a list. You can only have a list of ints or a list of chars. If you look back to the pair of things type defined earlier, you can have a tn tuple of 2 things, but those 2 things actually need to be of the same type, because pair of things is defined as taking a type level argument, and the tn tuple will contain 2 things of that type. Here in this listed example, we can have m set to be a tn tuple of 1 and 2, and m will have a type of pair of things, int. So kind simply describes how many type level arguments are needed for a given type to become instantiable. Kinds without the kind of star are known as higher kinded types, and there cannot be concrete values that have a higher kinded type. So to be clear, the lone char L has the type char. The type char has the kind star. The lone number 3 has the type int. The type int has the kind star. So types that require further type level arguments are again known as higher kinded types. List and pair of things have the kind star to star. Another level of star to star is added for each extra required type level argument. So int has a kind star, pair of things, int has a kind star, because pair of things has a kind star to star, pair of things int has had int applied to it, resulting in just a kind of star. So let's talk about some practical higher kinded types. We've already gone over list, which is a higher kinded type we've been talking about since the beginning of this course. But here's two more. The maybe type helps us handle a variety of uncontrolled and uncertain situations. For example, user input. We take in user input as a string, and then we might try to read that input to convert it into an integer. As we have covered, this operation is unsafe, converting a string value into some specific type value, like a number. So rather than setting some variable equal to the result of reading the string, we might set it equal to the result of some other function that tries to read the string, and if something goes wrong with reading that string, returns a nothing. So in other words, this magical function actually returns a maybe integer. The maybe type has two possibilities. It can either be a nothing, or it can be just a, where a is of the type supplied by the program. So in this example, we would have a function that returns a maybe integer. Then in our further processing, we can check if that function ended up returning a nothing, meaning something went wrong or the user supplied an invalid string, or it can just be a just a, and then we can look inside of that just to retrieve the value that was actually found. So the maybe type has a kind star to star, but maybe int would have the kind star. The either type helps us express information that is a variable type level structure. So in a language like Python, we can easily just have a list of many different values, all of whatever type we want. In Haskell, we cannot just have a list that has int values and then char values, but we can have a list of int char, meaning everything in the list has the type either int char, and then specifically each value is either a left or a right. And that left would actually be a box for an int value, and the right would be a box for the char value. This would allow us to express a list that has multiple values, and those values can contain actually an int or a char in practice. Furthermore, we can nest either types to be able to express data that can have any number of values that we wish.